This is the third in a series of videos in which I'm attempting to repair this second Wren executive computer system. In the first few videos I got as far as repairing a few faults, replacing a few ICs and getting the machine to start to go through the self-test procedure. However, it's failing on the second self-test, which is the first part of the video RAM. That's this DRAM over here in the corner, and it's failing to test that DRAM. The test is very simple. It just writes some data to the DRAM at various addresses, reads it back, and if there's an error in the read back, then it flags up the error. However, as I mentioned in the previous video, I believe this was down to failing ICs rather than failed ICs. I think it's just a signal level issue. I've mentioned in previous videos that ICs rarely just fail. They tend to degrade in performance over the years. And because machines like this were kind of pushing the technology a little bit, the clock frequencies were a bit high for the devices, and also the board layouts weren't particularly good with regards to high speed, then we tend to find that the mode of failure in these, at least in terms of failing to boot, can often be just a degradation in performance of the devices. And that's the impression I got. I have found some failed ICs, but replacing those hasn't resolved the issue. And using a scope to look around the board, I was finding that the signal levels on various buses and control lines were very marginal with regard to TTL operation. There are some large-scale devices on here, of course, that also tend to need certain signal levels to work properly. So the question, once you come up against this, is how to proceed. And there are various techniques you can use. As ever, I like to show different techniques when I can. My next step would normally be just to throw the logic analyzer on this and start looking at the buses. But before we do that, I just want to backtrack a little bit and show some methods that we can use to fully qualify whether my assumption is correct and this is just poor performance from one or more devices on this board. That's very different from having failed devices. Failed devices are fairly easy to track down because obviously the outputs aren't doing what they should, and it's fairly easy to spot that. It's much harder to track down a fault when it's either intermittent or the signals look reasonable on the actual bus that's not working. One method you can use if you feel it's a marginal issue and it's just a failing device you're looking for rather than a failed device is to see if you can get the machine to work at a slower clock speed. In general, the performance issues you get with ICs as they age tend to mean that their performance at high frequencies tends to be more marginal than at lower speed. So what I've done here is I've taken out the original crystal. So I've got the crystal here, it's a 12 megahertz crystal, and I've now got a signal generator hooked up to the input to where the crystal oscillator would go. So where you connect this is, in this case, this is a kind of ring oscillator that's controlled by a crystal, and I'm injecting the signal into the input buffer that is fed from the crystal. So in other words, this will still go through the same path, the same dividers. It's just that I can use a signal generator rather than the crystal. You need to take the crystal out, of course, so I've done that. I can now control the clock speed of the board. So what I'm going to do is try powering this up with a slower clock speed. Now, systems like this don't really work with the wrong clock speed if it's vastly wrong, but quite often you can get them to boot as long as you are fairly careful in the way you go about it. So what I'm going to do now is try to boot up the machine. I'll tilt the keyboard so you can hopefully see the test LED, that's the power LED here. And I'll start the clock. It's currently set to 5 megahertz. I'll power up the machine. The caps lock light has come on. It's going through the self-test. And it's finished the self-test and the light is on solid, so it's successfully completed the self-test. And if you look at the monitor, you can see you've got all this mess on here, but that's because the clock frequency is wrong. I'll start to increase the clock frequency. I'll take it up to 12 megahertz, which is what it should be. and we can see that the Wren is now up and running. It won't be running properly because we still have the same problem we had before, which is the devices aren't working correctly because we have at least one device that's underperforming. But what it does mean is that they're all fundamentally working. That is, they're able to switch. Otherwise we wouldn't have got through the self-test. They're working, they just won't work at the full 12 megahertz. Now that is divided by 2 before it goes through to the Z80, but 6 megahertz is still quite a high clock speed for this era of device. Now the reason I've done this is firstly to give me some idea as to what I'm looking for. So I'm not looking for a totally failed chip, I'm just looking for one that's not giving the correct output at high frequency. And we can see it's very stable, it's giving a very nice clear display, so I know that all things being equal, if we can find out which devices aren't keeping up with the clock rate, then we can just replace those, and that should get the machine fully up and running. This can save us a lot of time because we now have a better idea what we're looking for. What I'm going to do now is break out the logic analyzer. You've seen me do this before. It's really just testing the devices. I'll start with the buffer chips, that's most likely where the problems are. All I'm going to do is take a test clip, hook up a pod to the analyzer, and then I'll be testing the inputs and outputs of the buffer chips to see if the outputs match the inputs. And I can do that with things like the 240s, 244s, 245s, and that way I can test the entire bus set and control lines that are sort of going around the board, and they're the most likely ones to be causing this problem. And you can very quickly track down where those problems lie, no pun intended. Okay, so I'll start doing that. I may just show a few on camera, but mostly it's fairly mundane and boring, so I won't burden you too much with it. But as I say, all I do is clip the analyzer to each device in turn. I've got the analyzer set up with predefined test configurations for different device types. Run the board at full speed and then look for any mismatches between the input and output of the buffer. If I find anything, I'll get back on camera, show you what I found, and hopefully then we can replace whatever devices aren't up to scratch, and that should cure this fault. So I spent some time with the analyzer. I found a few buffer chips that had failed or were partly failing, so I replaced those. The test doesn't get any further, but the buses do now all seem to be behaving themselves. So the next thing to start looking at was the timing control, especially for the DRAM. And I don't have a schematic for this, so I spent some time kind of reverse engineering the way that the memory is used. And of course, because this is DRAM rather than SRAM, there is refresh circuitry and logic required for this as well. And for some strange reason, it's all driven from over here. And this controls the general timing for the machine, at least this is the source of it. Now, there was a lot of damage in this corner of the board because of the battery leakage. I had given the board a very good clean, but I'm finding sort of damaged chips in this area. So the sorts of things I'm looking for, if we look at the scope, that signal doesn't look too bad until I reset the machine. And then some of the signals on this device look extremely poor. So the problem I've got is I can't see a part number on this chip or the one next to it. And I do have another of these machines, so I thought I'd look at that to see what the component was. And it's exactly the same on that. The numbering has completely disappeared. I suspect it's down to battery leakage. I don't think the manufacturers have purposefully removed it. I think it's just the acids and whatever from the battery completely covered this part of the board, and they seem to have taken the part number completely off the IC. so I've got no idea what this IC is supposed to be. So what I'm going to have to do is reverse engineer this part of the system. And when I say this part, unfortunately this does seem to control a lot of the board in terms of general timing, so I'm going to have to spend some time trying to figure out what this component's supposed to be. This output, I'm assuming it's an output. I can't find, I've traced it through and I can't find any other connections that are outputs from other devices, so I have to assume this is the output. And the problem is, as you can see, if I reset the board, the signals coming out of here are very poor, and I suspect this is a major cause of why we're not getting proper timing going around the board. I haven't looked at it with the analyzer. What's happening is we're going into the self-test for the video DRAM, and although the DRAM itself seems to be working and I can read and write it successfully using the fluke, the system cannot properly drive it, and that's normally down to some kind of timing issue with the DRAM refresh, assuming that the data buses are all correct. But when we start seeing this sort of poor signal, then this is the sort of thing that at high frequency we're going to get major problems. So what I'll do now is, I won't do it on camera because it could be quite a tedious process. I'll try to figure out what this component should be. I'll put a socket in there and then we'll try a replacement component. If I can't figure out what it should be, then it might be a bit of a problem. But I'll have a look around, see if I can figure it out. I'll take it out, put it under the microscope, maybe I can see something that way. If not, I'll just have to try and figure out what it's supposed to be in there. So I took the device off the board. I still can't see a marking on it. I've had it under a microscope and I still can't see anything. I've examined the other board under the microscope and I can't see the marking on the same device on that board either. As I say, I don't think the manufacturers intentionally removed this. I think it's just the leakage from the batteries just etched the marking off it. So I had to start probing around trying to figure out what this device might be. So I was looking at the signals going into it. I was doing the same thing with the other board, and judging from the signals going into it, the signals coming out, and the other devices I can find that it's connected to. As far as I can tell, it is a 7400, so it's just a fairly basic 7-4 logic device, and as I say, it's just pure speculation, but without a schematic. I have to try something. If this doesn't work, then I'll attach the logic analyzer and do a bit more examination of the signals, but there's only so far you can go down this route. So I'll try a new device and see what it does. So I'll attach a scope to the pin that was giving us the very poor signals while I power it up, and if anything looks untoward, then I'll immediately power it back down again. But on this pin we were getting very poor looking signals, and I think that was contributing quite a lot to the timing errors we were getting, which is why it was failing the test. It wasn't really a memory failure, it was just the general timing issue that I was finding. Okay, so I'll power this up, I'll keep an eye on the scope, and if the signal looks bad I'll turn it back off again. Okay, well that looks much better than it did. That's more along the lines of the signal we'd be expecting to see, and in fact if I just move the ribbon cable out of the way, you can see that it has in fact completed its self-test. So that's taken it a big step further forward, and I'll just move the camera across. And you can see that the Wren has booted to the welcome screen. Now sometimes it can crash when we get to this part of the code, so I'll press the reset button on the board. It's a soft reset, so it does require the code to be running to actually do a reset, and then we should see a different message on the screen if the system is actually up and running. And we do. I'll try it a few times just to make sure. Well, that's quite a big step forward in getting this machine up and running. What I can do now is test the rest of the functionality of the main board. I can reattach the fluke, do some more in-depth memory tests, and then I can attach the floppy drive and see if the machine's at least trying to access it. I can't boot from floppy disk, of course. I don't have a working boot disk. Again, if anyone has a copy of the boot disk or the image file from it, I'd very much appreciate a copy. But that's it for this video. In the next one we'll look at attaching the floppy drive and reattach the fluke and do some more testing on this board. But as you can see, we're getting close to having the machine working.